Okay, you probably have already seen that I posted the link to the previous video. So if you are you want to review the content, you can review it on the Facebook group. Well, since last time, mostly the content were about reviews of previous concepts that you need to understand first. So well, you can went back to see those topics again if you want on how I explain those later on in the lectures. But I will try to be comprehensive, and if there are any related topics that you probably need to refer back to, I will put them into the content if necessary. Okay. Right. I think let's begin. For today's lecture, I have already started the recording for this and this as well. Okay, the device is ready. Test the chip. Okay, let me turn off the annotation. Name of annotator. Okay. Okay, let us begin. Lecture 3 is about the optimization, about how the machine learn patterns from data. Right? So we are going to learn a way to optimize the model, particularly if we have machine learning models that you need to train the weights or the model parameters so that the model would describe the relationship between the data set that you have between input and the output. Right. This is an optimization problem. In an optimization problems, we have an objective function here. An objective function. What is an objective function? Well, in optimization, you may want to optimize to find the optimal parameters. Such a way that the optimal parameters would provide the results as you want. It can be to minimizing the function or to maximizing the function. In our case here, because we are talking about machine learning, we are talking about deep learning, our goal is to identify parameters that are suitable for the model and minimize the difference between data and the predicted data. That means we want to minimize the objective function. Our objective function here, think about it as error function or loss function or the cost function with respect to the parameter x. And then this equation tells you that this is an argument, getting an argument of fx. Argument of fx is x, the vector x. And this x would be the x star, would be the optimal parameters that obtained from the minimal argument here. In the context of machine learning, this is data fitting. Right? We want to fit the data with certain functions. That certain function is fx function that we saw here. In other types of work, fx might be different depending on the task that we are talking about. For example, in unsupervised learning, fx may refer to the variation in the data and you want to minimize them. In supervised learning, fx might refer to the mismatch between prediction and the actual data. Okay, we want to minimize this fx and then to obtain the base parameters that will provide you with the matching between provide you with the lowest error rate or the lowest cost in your objective function. Okay, this type of problems can be seen in many applications, not just in machine learning. You can find it in physics, in finance, in other fields as well. Okay, in our case here, we will define this as the objective function. Okay, we want to, as an optimization problem, that is, we want to minimize or maximize the objective function. This objective function can be the cost function. If we are talking about the cost, like we can have a model explaining the cost of ordering products, and then we want to consider the best way to order products in such a way that you will minimize the inventory cost in the long run, right? That is cost function, and there are techniques that allow you to solve such a problem, like linear programming, integer programming, for examples. But sometimes the parameters, the solution that you want to identify, are the weights of the model. They are the things that will capture patterns between input and output, that will capture relationships, allow you to map the data between input and output. Usually this is described in forms of either loss function or error functions. These two explain the errors that the model might produce if it performs incorrectly. Okay, so we would have this objective function explained as fx. Then how do we identify if we have the if we have the function, we want to find the point that it is lowest, like this. We have a function fx. We want to find this point, this x prom. How do we do that? Right? How do we find the x prom here? One way is to identify the gradient, right? By take derivative of this fx function and set it to 0. Then you will get the lowest point. However, let me check. Right, you can get the gradient. Gradient would explain like the slope of this function, and you can see that where the slope of this function becomes 0, you get like the lowest point, right? If we are talking about just this nonlinear relationship and there is only one point, just one value, right? Just one point that gives you the lowest value, then the point that is lowest would have slope equals 0. But thing is not that easy in real life, because when you want to map between a bunch of data to the labels you have, many times in order to do so, there have to be nonlinear relationship, and those would create non-smooth error boundaries. Like instead of having this smooth fx, your fx might look like this. And there are multiple low. How do you know which one is the lowest, right? And that would create problems. Okay. So in order to identify the lowest point, you can see that we can take derivative of the function, calculating the f prime x, or this is the dfx by dx, or the dy by dx, the derivative that you have known in your undergrad level. This f prime x gives you the slope, of the function fx at the point x. And so that what does it mean? It means that this f prime x will give you the value that suppose you want to know the fx plus lambda, fx plus epsilon. This value fx plus epsilon can be approximated by the fx plus derivative, right, multiplied by the time, right, the small amount of time. This approximation allow us to explain the change in the value of data. So let's look at it this way. Suppose we have this function fx. Fx is 1 over 2 x squared. 1 over 2 x squared, right, has, when x is less than 0, 1 over 2 x squared has decreased, would be decreased, right? Decreasing when it approaches 0, moving down, and once it's past 0, it move up, right? Only when it is 0, then you have the derivative equals 0. Okay, how do you know that, right? Just look at this. This green line, like the green line here, indicate the f prime x equal x, and you can see that because f prime x equal x, you have this slope, right? This slope, and this slope indicate the y equal x, right? It's y equal x like this. So what does it mean? It means that after passing through 0 here, on the left hand side, you can see that the value that are valid for f prime x are all negative. Why for the right hand side they are all positive? Because like they would increase in positive manner, while they on the negative side they would have like a negative slope in terms of the derivative here. And at the point that x equals 0, the values of the derivative is 0. Okay, so you can see that that point equals 0 has some importance. When the gradient equals 0, we could have 3 different scenarios. Like the first one, it can be the minimum, right? Can be the minimum point, or this can be the maximum point, or it can be this saddle point. Right? The saddle point is like the point where the slope change from one like approaching it from this angle, and then it becomes 0, and then going into another angle here. So the point here would have 0 slope as well for the derivative. Right. So there can be like three types here. Okay. So at least we know that if we represent the function as the loss function or the error function, it is possible to identify the lowest point so that we can have like the minimum point and get the parameters out. When we have multiple input, when we have multiple parameters, we cannot just take the derivative of one variable with respect to just one variable. We need to perform the partial derivative. Suppose the parameters, the weight that we want to optimize, contains say 4 of them, then we need to perform partial derivative 4 times to get 4 equations. Right. So the partial derivative here, occur by xi of fx. This would measure how fx change with respect to xi, whether it would change in a positive manner or negative manner. Usually, if we have this fx, we can think about it as the vector. Take derivative of vector, we have this called the gradient of x, right, of fx here. Right, gradient of the vector x with respect to vector x of function fx. This refers to the change of function fx with respect to the vector x, which can have multiple dimensions. Okay. So in the multiple dimension, we want the point that satisfy all the criteria here. Right. We will take a look at the concept of gradient first, and then we will take derivative of the function that will be the basis form of neural network, the logistic function, and see how we can optimize the function, how we can optimize logistic regression by solving this equation. Okay, so let's take a look at the proof of the direction of gradient first, on how the gradient move. How do we know that the gradient would move in the direction that the error would increase in our case here, right? So we will perform the derivative with respect to the unit vector u. This would be we will try to identify this vector u, which would be the slope of the function f in the direction of u. So what we have here is that we will take the directional derivative to see the change in direction. right, of the function fx, and then add it with the alpha and u. So what does it mean? Just suppose we have in the previous picture, like we have the function in one dimension. Say this is x, this is fx, and then when we take derivative of x here, some x value here, x0, right, we would have the value here at fx0. What we are trying to do here is saying that, okay, we are going to find the function fx0 plus very small alpha and very small value u, which moving into the positive direction, right? Or just say just the small value u, because it is a unit vector in one dimension. It is just in one dimension. It's just adding the value, right? Direction is encoded in terms of the of the sign. All right. So, but for this one, we are talking about derivative in the u direction, because we have like multiple dimension, multiple axes. We can have like x, y, and z, and other like suppose that the network that we have contains 20,000 parameters. So we are talking about the error when changing multiple vector altogether. Okay, with respect to alpha, and then we are trying to evaluate when alpha is 0 to get the derivative, right? Finding this function. So what we are trying to see here is whether the gradient would change if we take a little step in the direction of u, and u go into the same direction of f. So we have to get the direction, we need to compute the gradient. This is curved by alpha, and then fx plus the alpha u, add just some minimal value of u to fx. Okay, and to see whether when we compute this, we can finding this by take derivative of fx in the direction of x, because this is like moving just a little bit, right? If you remember this equation, we are talking about if we were to add just a bit of value here, this would approximately equal to having the value here and then multiply by the time step, right? The step that you take, multiply by the gradient, right? The change. So using the same concepts, we are talking about moving into this direction just a bit. This would approximately equal to getting the gradient of fx, right? And then multiply by the vector u, right? When alpha here is approximately 0, because if you take a look at this, this is just derivative of the derivative of fx, and then you have some vector u coming in order to adding or going to that direction. So because it is a unit vector, it is equivalent to having the dot product between them. Okay. When alpha equals 0, it's like taking the limit to equal to 0. So in order to minimize that function, in order to minimize f, finding the lowest value of f, we would need to find the direction that f decrease, basically, because the reason that we want to identify the direction of gradient is to find the direction that fx change. So this idea is to find the direction that would decrease fx the fastest. So this will make the prior equations becomes the optimization functions. That is, we want to minimize what? We want to minimize the derivative of fx. We want this value to be as low as small as possible. Okay, we want to minimize this value, and also we have this unit vector as the direction. This unit vector, when you calculate the dot product with the fx, would indicate the direction. When you find the value of u here, it would indicate the direction that it would make the where when you add to x, it would make fs going to the lowest value. Okay. So this multiplication equal to the vector, actually is equal to vector multiplication. Take the norm of u here, and then take the norm of this directional vector, and then cos theta. The reason that I'm trying to do here is to show you that in order for this minimization to give you the best result, to give you the lowest value. Suppose that we know that here the size is 1, and this factor size here also some constant value. So in order to make this equation lowest, we know that we need to minimize cos theta. Cos theta is the direction between fx and u here. The direction between fx and u. So it tells us that in order to optimize in order to get to the solution fastest, you need to update x in such a way that it make this value lowest. And what values would make this one lowest, right? Well, we talk about something like this. We have this the gradient of x fx. Say suppose we have two-dimensional data and take derivative of the two-dimensional vector, we get the directional vector of fx look like this, and we provide with an say an imaginary unit vector, directional vector u, and what we want is to make it go to the fastest way, right, to reduce the error. And from what we are trying to do here, you can see that in order to get it in order to get this function to reduce the fastest, the best way is to go into the direction that that would minimize the cos theta. Theta is the angle between the unit vector that we are talking about, the direction that you will change parameters here, the direction that you will change parameters, and the gradient. And you can see that only when u goes to the same direction as the gradient, that you would get the value of cos theta equals 0, which is the lowest value. Okay, so this is the proof that the direction that you would be able to reduce the error would be going to the same direction as the gradient. Okay, once we know that, we can apply it to optimize for our error function. That is, we want to find the point that error is lowest. We can just take the direction of gradient, right? Going to actually opposite direction of gradient. Okay, and then we can use it to optimize for this nonlinear regression. Because if we have linear model, if we have an equation like 3x, let me use the red one. Say if we have equation like 3 of w1 plus 2 of w2 equal 5, and w1 plus 3 of w2 equal 1, and w1 minus w2 equal 2, something like that. We can use this pseudo-inverse, right? Pseudo-inverse to solve for the equation, to estimate the value out. Right? However, in our case, if the relationship here is not simply linear relationship, but rather we have nonlinear regression. That is, when we want to explain the relationship between x and y, it needs to go through some nonlinear terms, right? Nonlinear relationship. In this case, you cannot use the pseudo-inverse to solve for the final form, to solve for the parameters of the model. You want to find beta, these unknown parameters, right, that that would give you the best approximation of y with some error epsilon here that are uncorrelated random values. This is called nonlinear least square, in opposite to the linear least square that we saw in the previous lecture, that we saw that you can use pseudo inverse to solve. In nonlinear least square, right, we have the data like this, like a table here, just like the other problems. We have a data, this is target, and you have a bunch of x, right? But what we are trying to do is to fit this to the nonlinear function. This is the nonlinear function. Okay, in the nonlinear function, you cannot take derivative of the inside of the function. Right? So that we will see later on what are nonlinear function. Okay, so in order to fit the data to the model, in that case, we need to explain the model, the relationship between the data or y and x with respect to the model, which is the fx here, and then we have this error function, or this is the square error function. We have the summation of yi, the actual value, minus the predicted value of fxi beta square to eliminate the sign. And here would be the error function describing the matching between the actual data and the predicted data. Now this f, if it is nonlinear, if it is linear, there's a problem. You can use derivative in combination with solving system of equation and find the answer. That's simple. Okay, but if it is nonlinear function, for example, if the function is something like this, that is e to the minus x, no matter how many times you take derivative of e to the minus x, e to the minus x will stay the same, right? So this is unsolvable root, or sometimes the objective function can be nonlinear. And that means you cannot use a simple derivative because there might be like multiple laws here. Okay, so then how do we find the best parameters, or how do we find the lowest point out of this equation? How do we identify beta out of this equation, right? In order to do so, we need to use the thing that we proved earlier. That is, to find the lowest point, you must identify gradient. Once you know the gradient of this point, let's say you guess some point in the curve here, and then calculate gradient of this point. Knowing the gradient of this point, you know the direction at which the gradient increase, the direction that error increase, because we are talking about error function here. A direction that error increase, that means you can go to the opposite direction of the gradient, going to opposite direction of the gradient with certain step, right? And then after you hit the next point, then evaluate the gradient again, and then update the point, and keep doing that, right? Evaluate the gradient and update, gradient and update. This is the algorithm known as gradient descent. Gradient descent, in other name, it is called hill climbing. The gradient descent algorithm start from randomly guessing the point here, and then determine the descent direction, that which direction that the error increase, and then basically just take the derivative of the function, and then you know the direction at that point. Then you can go to the opposite direction, mean minus sign, right? Going to opposite direction and choose the step size. Usually you will have some constant value to multiply the gradient. Multiplying the gradient, and then update the point. Afterward, repeat the same steps many times until you hit the stopping criterion, right? Repeat the same step, determine the descent direction, choose the step, update, and keep doing that until you reach the stopping criterion, and that's it, the end. Okay, so once we know this pseudo code, I would say this algorithm step by step here, how do we do that mathematically? Okay, then we will look at how to do it in terms of coding later on. how to do that mathematically. First, you need to randomly guessing beta. Just random the value of beta. Then you need to determine the descent direction. In coding, just substitute beta into the ds by d beta. That means you need to get ds by d beta first. You need to have this. Function ready. It means that you need to take partial derivative of the error function before using this algorithm. I mean using calculus, take partial derivative like that. So you will have the formula to substitute beta into that formula. Afterward, then you choose some step size. This can be constant or it can be changed. Later on, we will see that when we learn about the optimization of deep learning. Then multiply the step to the gradient. Oh, don't forget to the opposite direction. That's why you need to have minus here. Then you can update this whole bunch to the beta t. Beta t denotes the parameter at the iteration t. Right? Then you have beta t plus 1. Then repeat the step going to determine direction and then choose a step and update and then keep doing this until you reach the stopping criterion. For example, the gradient is approximately 0 or you reach that many iterations, like 1,000 iterations, or you can have the gradient you can have the error not changing for how many iterations, then you can stop. So those are stopping criteria that you can choose. Okay, right, so this is the algorithm, the gradient descent algorithm. That means you need to use calculus to take derivative of the function, to identify the parameters, how you would update the parameters. And then it's just a matter of repeating the process to get the solution. Okay, any question here first? What I'm explaining here is a step like in this picture, that we are guessing the point and then keep going down the hill until you reach the lowest point, then stop. Okay, any question before we look at the how to do this in logistic regression in the actual machine learning? Any question here first, or anything you would like to talk about the slides that I have been showing you earlier? Okay. Okay, so the step looks like this. You can see that the hardest one is to derive here, to derive the error function. By deriving, I mean using calculus to take derivative of the function and get the formula, the equations of that derivative. Okay, last year there are some students that confused. They don't know that computer engineering need to use calculus. Yes, you need to use it here a lot as well. Anyway, so you need to use the calculus to take derivative to get the form. Then you can use that form in your coding to let the program learn the parameters. All right. So let's take a look at examples. This might clear up a bit. We will talk about logistic regression. What is logistic regression? Logistic regression is a machine learning models that train to learn how to draw a line. This line will separate the data into two groups. One group as one class, another group as another class. Okay, this is a classification problem. Right. We will learn how this logistic regression work next. Okay, so logistic regression follow this mathematical formula. In this mathematical, actually there has to be this locked as well here. I should use this. Using it, it will go away after I close the page. I should have fixed this a long time ago. Okay, Logistic regression explain the relationship between the log of odd. This is an odd ratio. An odd ratio is the ratio of the probability of the thing happening, h theta x, and the probability of the thing not happening, right? 1 minus h theta x. You can think of h theta x as the probability of the event will occurring, like whether the team will win, whether you get infected with a disease. So this would be the odd. The odd is the ratio between happening and not happening, right? The probability of happening and the probability of not happening. Taking log, we usually call this the log of odd. This would have, well, probability alone here would have the scale between 0 to 1. Okay, the scale here. So let's say if we were to have this h theta xi equal say 1 minus h theta xi. If this is 0.5, this would be 0.5. Then the odd, the ratio here, we call this the odd ratio. The odd ratio would be 1. If this is 0.9, this is 0.1, odd ratio will be 9. If it is 0.99, 0.01, you get odd of 99. If this is 0.1 and this is 0.9, you will get, well, 0.101 something. And if this is 0.01, 0.99, then you get 0.0001, blah blah, like that. And if you take the log of odd, this would map, log of 1 will be 0, log of 9 would be something about, I say, 2 something. 99 would be about, I don't know, 8. This is minus 2, 7, minus 8, something like that. I don't remember the exact value though. But you can see that this would map between the probability domain into some more like the linear domain, because you have both negative when it belongs to one class and positive when it belongs to another class. Right? Mathematicians use this way to explain, to kind of explain the relationship between the chance of thing happening and the regression terms. Okay, so instead of having the linear regression term, which is fxi equal the theta 0 and the summation of theta ixi. Theta are the parameters of the model. Then we now have the odd ratio here, the log of odd here, equals the linear terms. Okay, and for the logistic regression, the probability is from this one you can inverse the equation a bit and get the h theta xi equal 1 over 1 plus e to the minus fx. This is the logistic function, or in another name it is known as the sigmoid function. This function will look like this. So if you look at this function, if fx is 0, then we have the value here as 0.5, because it would become e to the minus 0. Then this will be 1. 1 over 1 plus 1 is 0.5. If fx is less than 0, if it is less than 0, you can see that the more the value is, the more h theta x would reach 1. So it looks like this in summary. Okay, this is the sigmoid function. Logistic regression use, I would say that deep learning use logistic regression as the basis node in the model, the sigmoid function as the basis earlier in the model, because this function has a nice property. The nice property about this function is that if you take derivative of this function, you will end up with the value of the function multiplied by 1 minus the function multiplied by xi. right? You don't really need to take derivative. You don't really need to have another form of the derivative. Just multiply itself with 1 minus itself and x value. Then you get the derivative. Is that true? Need to be. I need to show you here. Right, let me share it as whiteboard. Okay, so we are looking at this h theta xi equal 1 and then 1 plus e to the minus fx. Okay, so if we take derivative of curve of h theta xi curve by theta, curve by theta or curve by xi, I use here it's curve by theta. Okay, then okay, we know as well that this one has this fx equal theta 0. Well, maybe I should just merge it together. That would be easier. Right, I will just write it this way. Oops. Should I do that? Can I go back? No way. Okay. Summation I equals 0 to how many terms? I use n, right? To n of theta I xi. Right? Then when we take derivative of this, it equals to curve by curve theta of 1 plus e to the minus fx to the minus 1. Right? Then take derivative of this, you get from the derivative property, just putting everything right. It would be minus, because pulling minus 1 down, right? It's like undergrad level, pulling minus 1 down, then you get 1 plus e to the minus fx minus 2 square, and then curve by curve theta of the inside of 1 plus e to the minus fx. Okay, like this. And rewrite it a bit. Now you have 1 over 1 plus e to the minus fx square. And then take derivative of 1, you get 0. Derivative of e to the minus fx, for this one, you have the value of e to the minus fx. And then multiply by curve theta of minus fx. Okay, this is like take derivative of the inside of the function, right? This is the usual process when you take derivative of the functions. And then you can see that minus would cancel out with minus. So I have this e to the minus fx over 1 plus e to the minus fx square, and then curve of fx by theta. And according to the equation above here, you can see that when we curve it by theta, right, theta I, say curve by certain theta I, the resulting would be that xi that multiply with theta I, because when you take partial derivative of something, you treat the rates as a constant value. So derivative of the theta xi would get you the value of just xi. Alright. Now from this one, we can separate the terms. One is 1 over 1 plus e to the minus fx. Another one is e to the minus fx over 1 plus e to the minus fx, and multiply by xi. Okay, now you can see that the right hand side here is actually h theta x I. This one is, believe it or not, 1 minus h theta xi. Well, you can prove it by, say, 1 minus h theta xi equal, this is easier than just try to make it grouping something out. Right? This is like 1 over 1 plus e to the minus fx. So just multiply up, you get 1 plus e to the minus fx minus 1 over 1 plus e to the minus fx. And then that means e to the minus fx divided by 1 plus e to the minus fx equals 1 minus h theta x. Okay. So in the end here it get into h theta xi 1 minus h theta xi, and I should use 1 minute, never mind, this is the vector, and multiply by xi. Okay. So fine. So what does that mean? Now, it means that when you take derivative, the partial derivative of h theta xi, you end up with the function itself multiplied by 1 minus the function multiplied by the value of xi. Okay. Yes.
Where did the e to the minus fx go at the numerator?
For the numerator, you mean for this one?
Yeah.
For this one, right? Okay. Where does it go? I think you need to look down here. Look down here. Let me use stamp. Yeah, this should work. Let me erase this out to some confusion. Okay, look at this. This is e to the minus fx divided by 1 plus e to the minus fx. And I said that the whole thing here, not just down here, but the above as well, the whole term is 1 minus h theta x. Why is that? Look at here. Look at the lower portion here. This is 1 minus h theta x, which when you expand h theta x to 1 minus e to the 1 over 1 plus e to the minus fx like this, you can see that putting, you should use the different color here, right? Moving here, oops, not this one, sorry. Okay, right, the whole thing here, multiply it up, then you get 1 plus e to the minus fx minus 1. Minus 1 cancel 1, right? The remaining is e to the minus fx 1 over 1 minus e to the minus fx. That means the whole thing here equal this one, right? Equal the 1 minus hx, right? 1 minus h theta xi. Sorry. So what I did above was to substitute the first term with h theta xi, the second term with 1 minus h theta xi, and the third term is actually xi itself. So leave it like that. Right. So the nice thing about it here is that now we have the properties that associate the derivative with simple multiplication. Instead of taking derivative, instead of having to find the form of derivative, we can just multiply the function with itself and multiply with the value, and that's it. And then we get the derivative value out. Okay. Right. Then that's the properties of the nice property of sigmoid. That's why it has been used in optimization, because you don't really need to take derivative of this function. You can just substitute xi into the function, and then you get the probability out of that. Very nice properties here. Okay. Now once we know these nice properties, now we need to define the error function. But in our case here, because what we are trying to solve here is not a regression problem, so we are not trying to match between y and y hat, between the two y, between the predicted and the actual value. Not that. That's the regression problem. What we are trying to do is to solve for the best classification. And how to define the classification problem, right? We can define the classification problem based on this loss function, right? This loss function is called the binary cross entropy function, right? This loss function, this is called the binary cross entropy. Some of you may have seen this in the deep learning library, that you can choose to have binary cross entropy. But how does it work? Let's look at it. Right? Why does it have to be in this form? Right? Any of you can explain this for me instead of having me just explain it for you guys? Can you explain this binary cross entropy and how it works? Why yi here is the label. Yi can take the value of 0 and 1. Can take the value of 0 or 1 depending on the labels. Okay. And h theta x is the probability of predicting 1. Okay. Can you explain this to me? Anyone? Why is this function a loss function for classification problems? Turn on the microphone and then try to explain this to me, please, if you can. The hint is this. The label. And h theta x is the probability of predicting this one. And 1 minus h theta x is the probability of predicting 0. Okay. You can try it. You can practice speaking as well. This will be a good chance. Right. Try explaining this, please.
I'm not sure if it is correct, but we are trying to analyze it when we predict wrong. Because if we predict different, there are different classes for predicted one and actual class. It will be higher loss than if they go in the same direction, meaning same classes for true and predicted.
Yeah, that is actually correct explanation. You need to ask yourself first, what is the loss function? What is the thing that you are trying to do here? Right? What you want to do here is to make this j theta the as low as possible, because once you make the j theta very low, you get the theta that is that fit, right? That make the model fit to the data, more or less, right? That it can predict the correct patterns. So you want to minimize j theta. When you want to minimize something, it means that the function, if the function has low value, that would be better than when the function has high value. Right? When they create a function like this, you need to think about the contribution of value, right? Because that means if it is incorrect, it should generate positive value. If it is correct, then it should go into negative direction. Right? Let's try to analyze this. Suppose that the model predict correctly. What happens? If the model predict correctly, you get the value of, and then if the label is 1, let's begin with 1. If yi is 1 here, you get the value of yi equal, let's say this is the correct prediction, and we have the case of yi is 1, right? Then h theta x would be this h theta x, because if it is correct, let's say if it is perfect, then h theta x will be 1 as well. This would be 1. That make the log of h theta x to be approximately 0. Okay. Now if yi is 1, then 1 minus yi would be 0, and then that would make the whole thing here approximately 0. Okay, that is the case if so now we can conclude that okay, for correct classification, ideal case, if yi is 1, then j theta should be approximately 0, or I would say for j theta of that yi. Okay, j theta, the j of that yi, I don't want to write at j theta of that yi should be approximately 0. That's for correct prediction of particular yi. Now, on the other hand, if we are talking about the instance of 0, then yi equals 0. Okay, yi equals 0. This would be log of blah 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 whatever, and it would mean approximately 0. Or equal to 0, because the label is already 0, right? And then you get minus of 1 minus yi, which now is 0, multiplied by log of 1 minus h theta xi. In the case that we make correct prediction, ideal case, h theta xi here would be 0, because it's not the class 1, it's the class 0. So you get the log of 1, which get the value to 0. So 0 times 1, you get the value of 0. That means in the correct, entirely correct prediction, you get yi, when y equals 0, the j theta should be somewhat around 0 as well. All right, that's for correct classification. Now, if we talk about the case that the model cannot correctly predict the result, and we get incorrect classification, let me erase it first. Okay, in the incorrect classification case, you have when let me note it as the incorrect classification. When yi is 1, let's say we have very low value of log yi, say log of very low value. This is incorrect classification, and say 0.01 something here, and this would, because this is log of 0 point something, you get the value here, say maybe some value like minus 10. This minus 10, when you can see that when it hit with the negative sign here, you get the value as the positive loss. Positive value, which is undesirable in this case, because this is the loss function we are talking about. When and then when this is incorrect, right? So another incorrect classification, you get the value of 1 minus 1. This is 0, so the right hand side here will be 0 anyway. So now in the case of and also well, if yi is 0 and then it is incorrectly classified, then you get the same case here, that you get the positive value in the loss function. And this is why it's called the cross entropy, because you use the concept of entropy to determine that the classification belonging to the class that is supposed to be. Okay. All right. So you can see that the equation here explain the correct classification, and if it is incorrect, you get the value on the positive side. So what does it mean? It means that what we are trying to do would be to minimize this function with respect to j theta. Okay, how do we do that? Actually, I have the slide on the next page, but I will try to derive this by hand to show you first, so that you can see that okay, it's actually the matter of calculus to obtain the closed form. Okay, this j theta. Right, next page. How do I go to the next page? No, I forget that I have to click here. Sorry. Right. Then the loss function j theta equal 1 over n summation of I equal 1 to n for each samples. Then you get minus yi log of h theta xi and minus 1 minus yi and log of 1 minus h theta xi. All right. Now we have this loss function. Next is to take derivative of the loss function cur j theta by cur theta. Okay, take derivative of the loss function. We have I will do it step by step by starting with, because cur by theta, the derivative is a linear operator, so it can move inside until it hits some nonlinear function inside the summation. So what we have here is 1 over n, not related to theta. You can just ignore it. And even yi is not related to theta. Yi. Then we got summation. Oh, sorry. Cur by cur theta of log of h theta xi. And minus 1 minus yi and cur by cur theta of log of 1 minus h theta xi. Okay. I haven't done derivative for quite a while, so I'll try to go slowly. Next is to here, put it down here first. Summation of I equal 1 to n. This one we still have minus yi here. But do you remember what is the result of if you take d by dx of log of fx? This would equals 1 over fx of d by dx fx. Okay, so with these properties, now we will have minus yi over h theta xi d by cur by cur theta of h theta xi. And the next term would be, this would be 1 minus yi over 1 minus h theta xi, right? And cur by cur theta of 1 minus h theta xi. Sharp. Okay. Right. Now we have this one. quite long. Well, it's not that difficult because we know that derivative is simply the multiplication, right? So let's expand the term. 1 over n summation of I equal 1 to n. And for the first term, we got this minus yi over h theta xi from the above here. And the derivative of h theta xi, which is h theta xi multiplied by 1 minus h theta xi multiplied by xi. Right, this is for the first one, for the first term here. Okay, now let's go to the second term. Right, for the second term, we have minus 1 minus yi over 1 minus h theta xi. And then okay, I forgot the h theta. Oh no, the above, right? And then this term, right? So we have this curve by curve theta of 1 minus h theta xi. So 1 is just a constant. Throw it out. We have minus h theta xi. So that means what I will have here would be pulling minus out, right? Pulling minus out. And then we have this h theta xi, and then 1 minus h theta xi multiplied by xi. Okay. Then let's rearrange the equation so that it will make our life easier. Before that, let's see if we can cancel the division, the denominator with the numerator. Okay, we have this h theta xi to cancel. So let me go back one step, two step. Well, I used the wrong one. Let me. Okay. Now cancel it. Cancel this one because it's the h theta xi with the h theta xi, and 1 minus h theta xi is canceling with 1 minus h theta xi. So what do we have here? Now we have this equal 1 over n summation of I equal 1 to n of y minus yi and multiply by 1 minus h theta xi multiplied by xi. This is the first term, and the second term is plus because minus go against minus. We have the plus sign here of 1 minus yi and h theta xi and then xi. Right. So now we are at this point. What I'm going to do next is to multiply the terms, multiply yi and xi into the equation and pull xi out because both has the common xi. Okay, so here is 1 over n summation of I equal 1 to n. Then this would be minus yi plus yi h theta xi and then plus h theta xi, and then minus yi h theta xi, and outside here is xi. What I did here is to pull xi, the common xi out of the parenthesis and multiply everything in, and that will allow us to cancel the terms out again, as you can see that here and here, plus and minus. That means the remainings of this function, of this curl of j theta by curl of theta equal 1 over n summation of I equal 1 to n, and then we have h theta xi minus yi times xi. Right, that's it. Right, what we have here is the if you look at this, you can see that the partial derivative, the gradient of the loss function, is calculated by here. This is the difference between the probability, the predicted value, and the actual label. Right, the difference between the probability and the actual labels multiplied by the value of that x, multiplied by the value of x, and you get the gradient out. Okay. All of this has been described in this slide. I already have it derived here, but I want to show it you step by step how it was done. Okay. So since h theta is the value from the prediction, that means the value of the prediction at the current iterations, and y is the label, the target label. Okay, x is input. That means you can iteratively update the parameters using this gradient descent formula. That is, once initially you need to randomly chosen the value of theta. Theta 0 should be randomized or set to some value, and then you have to update this iteratively by subtract it with alpha of j of the curve j theta by curve theta, and this is the summation of all point. If you look at this is like summation of all point. You might wonder, where is 1 over n? It doesn't matter. 1 over n will be absorbed by this alpha anyway. So here is the summation of all point, and then for each point you need to the formula state that you need to subtract the probability at that iteration with the actual value. That difference need to be, or the delta, the gradient need to be the difference need to be multiplied with xi, and then sum them all for all point. Then you get the gradient, which indicate like errors, direction of errors at the point xi for the current parameters. Okay, so what I did is to use this equation, and then I generate a random data out, and I generate a random data out here, data xr, x1, and x2, and then and the equation to draw a line contain theta 1 and theta 2, actually theta 0 and theta 1, right? Just two parameters, right? So I update that vector using this formula, right? By having this predicted probability of each point minus the actual label of each point. You can see that initially there are many misclassified for sure. There will be many misclassified for initial iteration. These are misclassified, but once it update to the direction I did not control the direction. It's updated by itself. You can see that the curve move toward the point that it separates the data into two parts. Okay, and this is how logistic regression learn the line. It learn to distinguish between class, right, by optimizing the loss function, and then we can identify the best parameters for separating these two out of one another. Okay, any questions about the gradient of logistic regression before we begin, before we move further? This animation is drawn using R. I use the RGG animate to generate this one. You can use Python as well. I think there's like Python library to allow you to animate the stuff, but I don't remember what that library is. But if you want to try, this is GG animate in R, and what I did is just to write a simple R code that generate the data, a bunch of data out, and learn, and then starting by fixing randomly assign the theta, and then it would kind of iteratively update the value of theta, right, until say iteration reach 200, 100, I don't remember, and then it just stop and then capture the line every iteration as picture, and then put everything in GIF file, and so that you can see it adds animation here. Right. Any questions about the gradient or about this, about how it comes by? Why do you need to learn this? It is possible that, suppose that you work in a deep learning model, you might come up with your own architectures, your own cost function. And in order to optimize those cost functions, you will need to use the gradient descent. And this is how you derive for the parameters of the gradient descent. Okay. Well, let's take a break for say 10 minutes. I will continue at 7:30. The topics after that would be, well, can you add some constraint into the model? Rather than having just freely searching for parameters, can you add a constraint or put in some types of regularization into the model? Can you do that? How about linear regression? If we were to optimize it, how does it work? Okay, let's take a break first, and we will continue on in the mathematical concepts in optimization, in gradient optimization, when you want to include some of the parameters, some of the constraint into the gradient descent. Okay. If you have any questions, feel free to type in to the chat. Right? I will respond after the break. Right? See you at 7:30. Okay, let's continue. Before the break, we have learned it about gradient descent and how it can be used to optimize for the best parameters for logistic regression. Right. Sometimes, right, now we will talk about the kind of modification of gradient descent, which allow you to have different behavior of the optimization. Let's start with the constraint optimization. Sometimes what you wish for is that not just to optimize for the value of x alone, but you also have certain constraint. For example, you may say that x should be the value between certain properties, like between 1 and 0, for example. It should be probability. Or maybe x should have the value as low as possible. So you might have additional criteria into your model. This problem is known as constraint-based optimization or constraint optimization. In the constraint optimization, you want point X to lie within the region that you define, the region that will make the solution feasible. Right? Feasible means that it is within the range that you define. So how can you do that? Right? So this is like one way to help you in this is to just modify gradient descent so it take into account of the constraint. So in the search in the gradient descent, we can say that it can search from one point to another point, and then it can end up at a certain region, right? It can search just between this region. Otherwise, it need to get the best so far solution out. So that is one of the way. On the other hand, you can also modify. So for this one, line search means that like in gradient descent, that you need to update the parameter theta or to certain direction, right? The direction of gradient. Let's say if we have like the scope of theta, that it should be between 0 and 1. Otherwise, then if the update reaching the value lower than 1, then you can return 0. Lower than 0, you can return 0. If it's more than 1, you can return 1. That is the meaning of line search, right? So you can have certain constraint in that sense. On the other hand, there is another way to address this problem by another hard way, by converting the unconstrained optimization into something like a convert the constraint optimization into an unconstrained optimization. Right? How do we do that? Right? There is a method called this Kkt, the Karash, Kuhn, and Tucker, right? Which allow you to transform from the from constraint optimization. You can transform it into unconstrained optimization by change the constraint into the part of the equation, like this one. Initially, we would have the loss function as only fx. We have fx as only the loss function, but when we might have this constraint gx and hx, right? Gx is the equality constraint that it should equal some value. Hx is an inequality constraint that means that the value should be less than certain values. Then we can then put this constraint into the same loss function, into the same equation, by multiplying it with certain parameter. Right? These lambda and alphas are the multiplier. They are called the Kkt multipliers. Simply speaking, if lambdas are 0 and alpha are 0, then we have an unconstrained optimization. Right? If we have certain value of alpha, then it means that there will be an effect from the constraint in the main equation. The best way to explaining this is to take a look at the example here. Let's look at linear regression. Right? We have seen linear regression solved using pseudo inverse in the previous lectures. Now here is the linear equation, the error function of the linear regression. We have this ax minus b, right, square. This ax minus b square. We want to find the value of x. In linear regression, b is y, right, and then we have the coefficient multiplied by x minus y square. Right. Okay. So for this one, take derivative of fx. This is the gradient of fx would yield this pseudo inverse form. Right, this pseudo inverse form by take derivative of this one. This is a minus b, right? Pulling 2 down. So like take the normal derivative versus like vector calculus. Pulling 2 down, you got 2 and 1 over 2, and it cancel each one out. And then we have this ax minus b, the same ax minus b here. And take derivative of the inside by x. Then we got a, and the remaining here is a. So we have this a transpose times ax minus b. Multiply a transpose inside. We got a transpose times ax minus a transpose times b. right? And then if you equate this to 0, then we got pseudo inverse equation, right? Like last time, that then we take inverse of A transpose times A, multiply the other side, you get the solution. If you remember, by take derivative of that and then equate it to 0, and then we can move it to the other side, equal A transpose B, and then multiply inverse. Then you get the solution of linear regression. And this is what we have talked about last time. But let's say, suppose that there is a constraint that we want this x transpose times x, where x is this constraint is a unit vector constraint. That means this multiplication must be less than 1. That means the size of the vector cannot exceed the unit vector. It has to be at most unit vector, the size of 1. So this can be translated into the constraint in an equation like this x transpose, because if you move -1 to the left hand side, then we got this as Kkt suggested, we have this hx, right? This hx less than or equal to 0, and we can put hx and alpha here. We have this hx and lambda, never mind, just one parameter, lambda here. I think they try to make this equal 0, but well, never mind that, less than or equal 0. So you got some multiplier here, and the constant multiplier and the constraint in this form, and it is combined with the loss function. Now the loss function contains both error and the terms related to the size of the vector. That will make things complicated. Like it will, because in this case we need to find the value of x that minimize L. Right? We need to find min x, value of x, and then it has to find the value of lambda, right? That maximize the value of lambda, and then maximize it for the value of lambda here, and minimize it for x. So we want to now first, if we differentiate it with respect to x, we differentiate the L x lambda with respect to x. That means we would have this d by dx, right? And so we would have the same one here, d by x, and derivative of this by x, this is like x squared. So the resulting would be this x squared. So it pull 2 down, you have 2 lambda x as the result. Here we got the same result plus 2 lambda x. Grouping x together, and then do the same thing, move A transpose B to the other side and multiply the inverse, and you get this as a solution. That means in the case of having constraint that transformed into terms in the unconstrained optimization, it changed the solution of linear regression by adding you can see that this is a constant value by diagonal value, right? Lambda multiply 2 and then multiply I is actually a diagonal matrix, adding to A transpose and A, and then doing the same thing here. Okay, this is for x. You can optimize for x in this way. How about lambda? Right? How do we choose the value of lambda? Lambda needs to be chosen by also performing gradient descent, and then we would have this gradient descent lambda, the x because taking derivative of this by lambda would yield only the inside here, right? X transpose X equal -1. And if you were to equate this to you can see that by taking derivative of this, you have this value, and then we can use this value to update the value of lambda, and that's it. We have the two equations that can be used to update for one to find the parameters here, right? But to find the parameter here, you can see that we need to use lambda here. So you need to kind of iteratively update the value of lambda to find the best value of lambda that will be used, so it would affect the derivative in the solution forms. Okay, so this is how you can transform the unconstrained the constraint optimization into the unconstrained counterparts. Okay, so like the first extension of gradient descent by including something in. Now you see later on in the regularization lecture that we can include some more thing to control the model, so that it would not be overfitted. Okay, the second extension of gradient descent is that why not using the second derivative as well. Let's look at some examples here. Okay, so when this is a quadratic equation, right? Take derivative of this quadratic equation. We got this dy by dx. Actually, is this one, right? So at x equals 0, let's dy by dx here would be 2ax plus b, right? Dy by dx equal to ax plus b. If we substitute here value of x0 inside here, value of x0, the difference between this, which is origin, right, and this point is x0 minus b over 2a. So what does it mean? It means that suppose we have this, we have x0 put in here, and you can see that we have to move on to this direction, right, step by step. We know that this point, the value is 2x0 to ax0 plus b. Then if we were to perform the second derivative, right, the second derivative of the equation, we would get this from this one. Second derivative of this function will yield 2a. Okay, this 2a. So the idea for this method is that you can jump to the solution faster if the step is take into account of the second derivative as well, by putting the second derivative into the denominator. You kind of enhance the step depending on the change. The second derivative itself is the change of the gradient. Okay, and this method has been employed in the Newton method for optimization. Okay. Newton method for optimization would update in this scheme. We would update the parameter theta. This is theta k. Parameter theta k by updating it with the gradient. But rather than using just the gradient alone, you can divide it by the change of the gradient, second derivative here. Newton approach would kind of, instead of here the gradient descent, it would go into the steepest slope. The steepest slope would go into this direction. Newton approach would take into account of the change in the gradient as well, and it kind of make this go up faster, right, to the direction. Okay, So this is kind of an extension that you can use second derivative beside using the first derivative to go into that direction. You can use second derivative to adjust for the step size so that it can take like larger step size. But that is actually a better way, which you see that in the lecture on the optimization, that there is a method called the moment. You can use moment, the momentum, to control the step size rather than using this just second derivative alone. Okay, but nevertheless, there's this type of concept that you can extend like the steps. You can calculate the best size of the steps by using second derivative to help, and it will be faster. But faster might not be the solution, and that is because the problem with gradient the problem with the gradient descent is that it doesn't guarantee that you will reach the global optimum. It is possible that you have this unsmooth space and then it can go fast, but it can stuck with the global optimum. So there's another extension to the gradient descent that try to modify the model, so that try to modify the method in such a way that it has the random exploration inside the method as well. And that technique is actually your assignment, the stochastic gradient descent. Your first assignment is to implement the stochastic gradient descent. This is similar to gradient descent, except that you are learning the dataset that is sample. So each iteration, rather than using the whole dataset, you sample just a batch of that, just some like 10%, that like subset of the whole dataset. Right, so the idea is to first choose initial vector for the solution, then repeat until you hit the stop, right? But instead of just calculating gradient, you need to randomly sampling the data from a larger pool, right? Randomly sample it out, and then use that data to calculate the gradient. We call that the stochastic gradient. Multiply with step size, update the theta, and keep on going. Right? So the step will be longer, but with exploration, hopefully, it can reach the better point. Right? It can avoid hitting the local optimum and hit the actual optimum. Okay, so this is stochastic gradient descent, the SGD. SGD is implemented in Keras in PyTorch as one of the standard technique that you can use to optimize the deep learning model. Right. So yeah, this is the end of the lecture, but that will be this will be your first assignment. Let me show you the assignment that you have to do. I haven't changed the date yet, but I will post it soon. Right, this is an assignment. The submission would be in 2 weeks. You have about 2 weeks to do the job here. So here is the equation for the logistic regression. So again, I asked you to do the logistic regression, but instead of having just that, we would add this rich regression, the rich criteria. Right, the rich criteria, this lambda and then summation of W of the weight square will reduce the weight. So instead of having any values of the weights would be reduced as much as possible because it is part of the loss function. This is called a regularization process. Adding the rich criterion, this is called rich criterion, one of the regularization criterion, to the error function, it means that you need to take derivative of this error function with respect to this one as well. That's why the task for you here is to first prepare the data. Need to first prepare the data, doing the one against the rest strategy. Okay. Second, This is important. You need to formulate the error function. You need to formulate the error function. The error function will be the the loss function that I explained it. But now you have this rich regularization criterion as well. Thirdly, right, you need to derive the gradient of the error function and then implement the gradient using the dataset that you have there, and then modify it so that it becomes stochastic gradient descent, right, by just randomly sampling the output, randomly sampling the dataset, and then train the model. And then try to test the model to see the effect of lambda, like setting lambda to low value and high value, what would happen. And also test to see the effect of proportion of the task 5. Right. So this is all of the work that for this assignment. Right. Any question about this? Have any question about this? When do you want to submit the work? I'm flexible. According to the schedule, you have another. Let me check. According to the syllabus, this is what I would like to do is not that. According to syllabus, you will have this time you learn about gradient descent, next machine learning, no homework, no assignment, deep neural network, no assignment, right? Or will there be an assignment? Yeah, there will be an assignment in the deep neural network feed forward, but this will be an easy one. So you got about 2 weeks to implement this. Okay, you need to submit it before the next class, before 8th of September. Okay, and these are all the tasks that need to be done. Any question? Okay, the mistake that were made last years, some students got confused on this, how to derive the gradient of the error function. What some of them submitted was to use Keras, to use scikit-learn to do the job. But that's not what I asked you to do here. What you need to do here is to derive for the gradient, right? Derive the equations of the gradients, and then use that equation to perform optimization, to perform gradient-based optimization, and then extend that to the stochastic optimization, stochastic gradient descent, and observe the results. And that's it, I guess. Okay, do you want to more explanation regarding this assignment, or everything is okay? You can do it now. I will share the date. This is from the last year. I will share the date to the 8th of September. This one is 14, not that, right? The 8th of September for this one. No question? All right. Yeah.
Can you explain the linear regression again, please? In
Okay.
in Kkt.
Okay. For this Kkt, the idea is to change the constraints into some part of the loss function. Okay, so for the linear regression, this is an error function of the linear regression. Left hand side here is the predicted value. Well, if you remember, for this one it would be the linear regression. For this one it would be ax equal b or ax equal y, but rather than having this, we change it into the error function. So this would be the predicted, and this one would be the actual. Then down here is the derivative of the function, right? Pulling 2 down, cancel it out, take derivative of the inside of x, you get a, remaining a here. So you got a transpose times the whole thing here, and this equal to some form like in pseudo inverse. Now when we add this constraint, additional constraint into the equation, this constraint is that the vector that you add in, right, this vector that you want to optimize should be less than 1. That means when you multiply it, you got the size. If the multiplication is less than 1, that means the size of the vector is less than 1. If it's equal 1, then it's a unit vector. Okay, so to do so, we add this inside. Actually, this equal, so this like lambda of x transpose x minus 1, right? If x is unit vector, then this would become 1. But if x is larger than 1, more than unit vector, it will contribute some loss. Okay, for this one. So in order to solve these forms, so for these terms, we need to solve this problem. Minimize Lx, maximize it for lambda. Okay, we want to find these forms. So how do we do that? Because there are two parts of this. Actually, you can see that it doesn't just contain fx anymore. So if we take the derivative of this, there will be this unknown as well that we do not know what value it should be. Okay, so first, if we take derivative with respect to x, then we get the value of x, pulling x together. So take derivative here, you get this one from the delta x fx, and this term is from x transpose x minus 1 and lambda. Okay, then I will pull the x together, and then you got this a transpose a plus 2 lambda I x, because 2 lambda cannot exist alone with matrix. It need to have I as well, otherwise it cannot be added together with the same dimension. Okay, and that minus a transpose b equals 0. So once you move a transpose b to the right hand side and then multiply this with inverse, the resulting is this one, the inverse of the a transpose a plus 2 lambda I inverse, right, and a transpose b. So it like a little bit modification of the pseudo inverse, and you can see that okay, you need to have some 2 lambda here. However, from the optimization, we still do not know the value of lambda, whether it should be what value. So what we can do next is to optimize as well, find the magnitude of lambda. How the lambda can be found, the value of lambda can be found by taking derivative of the error function with respect to lambda, and then we get this term. This term is what? It is actually telling you that lambda should be the difference between the size, right, x multiplied by if x is more than 1, it's not a unit vector, then this difference will result in some positive value, and that some positive value will be added to this value, and this will modify the matrix here to yield different value of x. Okay, so when you update it, it will affect x. Now if x here is 0, x here is x here is 1, then you got this value equals 0, and that would result in no change in x. That means if you iteratively updating lambda, right, it will adjust the value of x until x becomes stabilized. Once x becomes stabilized, then you got your solution there. Right? This is the way this is how it works here for Kkt plus linear regression. So in the end, x will be a unit vector and will be the solution of these equations. Okay. Right. So for your assignment, I would suggest you do it as soon as possible. It took about, I would say, 2 or 3 days to do that. Right? You need to derive it. It takes some time to derive that, and writing code to optimize for the parameters. It also takes some time, not long. Right? Once you have equation, it's a matter of repeating, updating of that value out. Okay. Let's call it a night because, well, the computer alerted me that I ran out of space for recording video, otherwise everything will be thrown out. I will try to edit the video and post into the group as soon as I can. Okay, so have a good night for today. For tonight, see you again next week, which will take a look at another topics, the basic of optimization of machine learning. Okay, so see you guys then. Take care.